So I'm going to present a slightly different sort of genetic biocontrol, vector biocontrol method. And I'm just taking you through how it all began and what complexities are involved until you reach a stage where you do a field trials. Because now for us, we are in the field trial stage where we are, actually we have finished some of the field trials. We are now going to look at the epidemiological impact of the technology. So some of the slides I'll try to rush through because of time. So this project is a huge project. I think it started way back in 2010, and there are a number of stakeholders involved, and it has got a lot of team members who are involved for it to be successful. So this is just the outline. I'm just briefly going to give a background on the situation in South Africa and why we ended up looking for complementary vector control tools, then why we chose the SIT, then the implementation plan, and our implementation plan involved research and development, field trials. Then I'm going to take you through the next phase and also our food for thought for using transgenic sexing strains as part of the project. So I think South Africa, in terms of reducing malaria burden, I think it has gone a long way. So for formal malaria control started in the way back in the 1970s when IRS, I think South Africa was the first country to introduce indoor residual spraying, which is based on that mosquitoes rest indoors, they feed indoors and bite and rest indoors. So this is just the journey we took. We had so many challenges, but what is important to note is that despite all this effort, we have never been able to completely eliminate the transmission. So there are a number of issues which are involved why we haven't sort of reached that last mile. So this is just a summary of some of the challenges we have faced, why we actually need complementary vector control strategies. So we have seen through research that there is what we call development of insecticide resistance. So when we started in 1996 to do thorough monitoring of the population, there was no resistance, but as time goes on, we have observed a number of resistance to different classes of insecticides. So all the available insecticides, except maybe the new generations, most mosquito populations have developed a resistance. Then we've also seen that when you eliminate what are termed your major vectors, you end up you're creating a selection pressure, and you're actually bringing other secondary malaria vectors. So it is also a challenge for you to eliminate malaria. The other situation is that there is also vector behavioral change, because you are exposing these mosquitoes to insecticides. They will try to a way of surviving. So instead of biting indoors, they end up by biting outside. And most of our current control tools are targeting indoor biting and resting mosquitoes. So you would obviously not reach your elimination goals. Then the other issue is the operational failure. As you reduce your cases, it is very difficult to manage your control programs, especially if you are using IRS. So there are a lot of operational failures which are actually driving the ongoing residual malaria transmission. So first with all these challenges, we tried to look at the various emerging tools which are available, and we had a number of them which we can possibly use. But after scanning the regulatory issues, we ended up trying to select one which we will go with. So we selected the sterile insect technique. So the technique is quite simple. It's just rearing your mosquitoes in millions. Then you separate your males from females. So this is done, females are the ones which are responsible for transmission of malaria. So you have to eliminate them from the production line so that you remain with males only. When you remain with your males only, you sterilize your male using irradiation. So you can either use gamma irradiation or X-ray irradiation, so that you induce mutation in your gametic cells, so that in the end, when your male mosquitoes are released in the wild and mate with natural females, or native females, those females will produce eggs, but those eggs will not be viable. So with time, you're actually reducing your population size, and at times you can actually eradicate your population. So this is the general principle of your SIT, or this genetic-based method of vector control. So the project actually started way back in 2010, so it shows you how difficult it is to end up with a vector control product. There are a number of issues which are involved. So we started in 2010, where we tried to identify the presence of what we call building blocks, which will enable you to do your SIT. Then we also did extensive stakeholder mapping and mobilization to see who are people involved who are going to be affected. Then from there, we actually went to phase 1. So we used a phase conditional approach, where if phase 1 doesn't work, we will not proceed. So we had, so far we've done 3 phases. And what is important is, why we are here, is the communication aspect, which I will try to go into details. So we discovered that, for your public intervention to be accepted, there's always a barrier to new technology. So we discovered that the acceptance of any intervention depends on the knowledge and understanding of the project or the technology by the community. So we really tried to work with the community before we even start the project, so that we really understand what their concerns and their fears, and where we can work with them to develop the technology. So we actually followed a very rigorous process. So the first thing is that we identified the areas we wanted to do this technology. So we looked at a number. Do we look at an entomological aspect? Do we look at epidemiological aspect? Do we look at a place where people are able to accept the technology? Then after that, we started initiating our community engagement activities. So the first thing we did was to characterize and build knowledge of the community, its diversity, and what are their needs, and because their needs are also dynamic. Then after that, we set out our goals of the project, and we did this together with the community. Then we started providing them with information, and this was through different road shows which we ran, so that we can engage the community. Then after that, we did what we call a CAP survey, just to really understand what the community know about the technology, what the community know about malaria vector control. Then after that, we then identify and mobilize and develop community assets and capacity. So we actually worked with the community to develop our communication strategy. And I'll just quickly go through that. So one of the most important things we did was the CAP survey, because it is the one which gave us what really the community understands, and if we were to put in a new strategy, how they want us to communicate with them. So we did a number of engagement activities, including various radio interviews, national radio and community radio stations. We visited a number of public health facilities and used public health officials to communicate our message. We also visited a number of schools in the areas we had chosen, so that we can engage the children, who in turn went to engage their parents. We also did door-to-door campaigns where we tried to distribute pamphlets, getting to understand the fear of the community. And we also ran a number of road shows where we're doing voluntary malaria testing and treatment. So it's just going to a community, public place. We set up our tents. We invite people for free malaria testing. If you are positive, you get treatment straight away. And if you're not, we start doing community education. So after all this, we ended up knowing that there is a certain way for engaging this particular community, because just using pamphlets with technical information was not going to work, because of the background of the community. It's a rural setting, and most of the people were not very literate. And when we really worked with the community, they told us that this community is, in terms of their culture, they really like their music, and there's a particular type of music they call Maskandi music, Maskandi. So what we did is to identify their most favorable artists in that community. Then we worked with that artist to develop a song based on the information we have given. And this really worked wonders in terms of trying to communicate the message. And what we also did is we actually engaged the local leader and also worked with schools and the radio station to develop, so we developed some dramas which were played on radio almost on a daily basis. We also engaged local schools and gave them our pamphlets, and they developed a drama, and we had a competition so that they try to develop their own message based on the information we had given them. Actually, we also ended up using the chief to give the prizes for the best school, which developed the best drama, which had an effect on the community in terms of messaging. So the key outcomes on our community engagement that when we did our cross-sectional survey after the exercise, we saw that there was an increase in knowledge in our technology. And we also got community participation when we started the project, and also when we started doing our actual releases, we actually had better uptake. And generally, in terms of health-seeking behavior, we also saw that there was a bit of change compared to an area where we didn't do this exercise. Then in terms of the actual work, actually we started, like I said, with field site selection. So this technology worked best on an isolated mosquito population. So we had to look for the best sites, and we ended up identifying one such site. And after identifying the site, we needed to have what we call baseline entomological information, so that when we do our intervention, we really know that this intervention is working. So we identified 3 different sites. So the first site, we used it as an intervention site. Then we had 2 control sites, the one which is proximal to the intervention site, the other one which was distal to the intervention site. So when we were doing the baseline data gathering, we just did field collection, then we processed the mosquitoes for various entomological indicators. Then we also looked at the seasonal variation, and we also looked at other entomological indicators, so that when we do our intervention, we see whether this changes or not. So the key outcomes when we did our data gathering is that we ended up discovering that there are actually a number of entomological factors which are driving the residual malaria transmission in South Africa. And through the project, we also worked with the malaria control program and ended up developing a surveillance system that we have now transferred to the malaria control program. And we actually capacitated the community, and we also have a number of infrastructure development we have done through the project. So these are some of the key publications for those who have want more information about the baseline surveys. So the next step was for us to sort of fill the scientific gap. So we, like I said in the introduction, that this strategy actually requires the separation of males from females, because you are only allowed to release males. So your sex separation strategy should be almost 100% efficient. So what we did, we developed a sexing strategy. So it was just a simple procedure. We had a colon which had deodorant resistance. So we had to translocate that deodorant resistance from the autosome to the sex-determining chromosome, so that when you expose your eggs to that particular insecticide, you kill all the females and you remain with males only. So we actually achieved a 100% sex separation system. Then we also wanted to find out that if we irradiate these mosquitoes, at what dosage should we irradiate? So we also did a number of experimental studies to do that. And we also wanted to see if these mosquitoes are irradiated, do they remain competitive enough to mate with the wild ones? So the key outcomes there is that we managed to develop a sexing system which is almost 100% efficient, and we determined the irradiation dose which induced sterility to the natural population. And we demonstrated that our males are capable of competing with wild males for the wild females. Then the other step you need to do is you can't just release mosquitoes. How many mosquitoes do you need to release? So you need to understand what is your population size in the area you're working with. So we actually did what we call estimation of a population size using mark release recapture exercises. So from that, we discovered that per every hectare, we've got approximately 9,000, and based on the competitive index we had found from the competitive assay, we actually want to overwhelm these mosquitoes by 3 times. So per every hectare, you need to release about 27,000 males for it to be effective. And we also saw that, how do you do the releases? We also saw that our males naturally don't have a large dispersal distance, 58 to 86 meters. So this became useful. At what interval should we release our males? So it was based on their dispersal distance. And we also see that these males, after we irradiate and mark them so that we can identify, they were able to locate natural swarms and mate with natural females to induce sterility into the wild population. Then the next step was for us now, how do we produce millions of mosquitoes? So you needed to develop ways in which you can mass rear your mosquitoes so that you are able to have that 27,000 mosquitoes per hectare you need to release. So we developed we had various scenarios to check what cages can we use, how do we blood feed these mosquitoes, how do you rear them until they reach adults, and make sure that the process is standardized. So based on that, we ended up, with that information, we ended up building a mass rearing facility which is capable of producing 1 million sterile males every week. And we also developed our workflow procedure based on the different experimental work we did in trying to fill the knowledge gap. So we actually managed, the key outcome on all that is that we managed to build the first African mosquito mass rearing facility. It is now being used as a reference center for SIT projects. And we also managed to optimize the different workflow procedure for rearing mosquitoes, and this can be used as a template for the current GMO gene drive push. So then we also developed our mosquito handling and transportation in the release procedure, because you need to transport these mosquitoes to your field site, and how do you do that? So we developed that, and we also optimized the transportation procedure, and we also developed the release protocols. And finally, we actually did the field trials. So this is how the field trials were set up with intervention arm and 2 control, and those were the key outcome measures we were looking for. Then this is how we actually released based on the dispersal distance. So those are the release points we had. And this is just the process of mass rearing. You start with eggs, you rear in your larval trays, and you separate your mosquitoes. Then you feed them on your larval diets. Then you take pupae, then you seed into that. Then you irradiate. Then you transport to the field. Then you do your releases. Then you do monitoring and evaluation. So there are various ways you can do that. Then we actually managed to, so these are the key results for the findings we found. So because of time, I'll just quickly browse. But the releases were actually impactful on the entomological aspect. We managed to reduce the population size compared to the control areas. And now the next stage is now we want to look at the epidemiological impact, and we have got our study design, and these are the secondary outcomes we are going to look at. So we can discuss further if you need more details on how we are doing this. And we are also developing a transgenic strain, which is more efficient than the current strain we are using. Thank you.